Hi, in this short video I'd like to address one simple question: what is the pH of a 0.1 molar solution of acetic acid? In the process, I'll touch on some related concepts: the nature of carboxylic acids, residence, pH, and acid-base equilibria as defined by the equilibrium constant Ka, or the acid dissociation constant. So let's get going. Acetic acid is a carboxylic acid with the structure CH3, C double bond O, OH. It's the active ingredient in vinegar, and it reacts with water to form the acetate ion, which has the structure CH3, C double bond O, O minus, plus the hydronium ion, H3O plus. In this sense, this is an example of a generic acid-base reaction because in this instance, the acid, or acetic acid, reacts with the base, or water, to form the conjugate base, acetate ion, plus the conjugate acid, hydronium ion. And the equilibrium constant for this reaction is controlled by Ka, which is Ka is, in this instance, CH3, CO2 minus, H3O plus, divided by CH3COOH. Now, acetic acid is in fact a weak acid, and it's a weak acid because it only dissociates to a very small extent. The equilibrium lies on the left-hand side of this equation. And numerically, this is 1.8 times 10 to the minus fifth. So that's a weak acid. By comparison, HCl is a very strong acid, which has a Ka of around 10 to the seventh. So about 12 orders of magnitude stronger than our very weak acid, acetic acid. For simplicity, I'm going to use some common abbreviations. Acetate ion will be known as OAC minus. Acetic acid will simply be HOAC. So in the next derivations, I'll be using these two related symbols for the acid and the conjugate base form. So our equilibrium is HOAC plus H2O is in equilibrium with OAC minus plus H3O plus, where I'm using the symbolism of a larger arrow pointing to the left-hand side to indicate that the equilibrium lies well on the side of the reactants. And so also notice that I'm inserting the abbreviations HOAC for acetic acid and OAC minus for acetate ion. And so the big question is, we want to know the pH, which is to say we want to know what is the H3O plus concentration in a solution in which the concentration of acetic acid is 0.1 molar. So to answer this question, we'll write out a small table that illustrates the extent to which the concentrations of the reactants and products changes as the system approaches equilibrium. And we'll do this starting from an initial concentration, a changing concentration, and an equilibrium concentration. This is sometimes referred to as an I.C.E. table. So in the beginning, our solution has a concentration of 0.1 molar in acetic acid. It has a concentration of 0 molar, practically speaking, of acetate ion, and it has a very low concentration, again practically 0, of H3O plus. Now, looking at this situation, we can see that Q, which is known as the reaction quotient, is equal to 0 times 0 divided by 0.1. Now Q is less than K in this instance, and that tells me that the system will shift, the composition of the mixture will shift in such a way that we will make some products. We will make acetate ion and H3O plus at the expense of acetic acid. So, as the acetic acid concentration decreases, let's say that the concentration decreases by a unit x. This means, from the stoichiometry, that the concentration of acetate ion will increase by x, and the concentration of H3O plus will also increase by x. And you can see this from the stoichiometry because we have a 1:1:1 ratio of acetic acid and acetate and H3O plus in solution. And so the amount by which the acetic acid concentration decreases is exactly equal but opposite the amount by which the concentration of acetate ion and H3O plus are increased. And so at equilibrium, we have 0.1 molar minus X and X and X. And from our definition of Ka, we would say that Ka is 1.8 times 10 to the minus fifth, which equals OAC minus times H3O plus divided by HOAC, or X squared divided by 0.1 minus X. In doing this, I take the concentration values of acetic acid or acetate ion, the concentration of hydronium ion, and the concentration of acetic acid, and put these into my expression for Ka. I get this expression, X squared over 0.1 minus X. Now, we're very close to our answer. We eventually want to know the pH, and so the pH requires that we know the minus log of the H3O plus concentration, and so we need to find out basically what is the minus log of X. From this equation, we can say that 1.8 times 10 to the minus fifth equals X squared over 0.1 minus X. And if you have a sufficiently complicated calculator, you can solve this problem. But if we think more logically for a moment, we can simplify this expression really quite a lot. We already know that acetic acid is a weak acid, and it's a weak acid because Ka is small. And now because Ka is small, the acid won't dissociate to any great extent. In other words, we could say that this whole expression, 1.8 times 10 to the minus fifth, is equal to X squared over 0.1, because 0.1 minus X is about equal to 0.1 if X is much, much less than 0.1. And generally speaking, with weak acids, this is a good approximation to make, and it will simplify the calculation of our pH. Now we can go through the math and show that in this instance, X is 1.3 times 10 to the minus third, and that equals the H3O plus concentration. It also equals the acetate ion concentration. And now for the pH, pH equals minus log H3O plus, or minus log of 1.3 times 10 to the minus third, or 2.87. So let's recap a bit. We started with an equilibrium. Our equilibrium was acetic acid plus water is in equilibrium with H3O plus OAC minus. This equilibrium constant, the equilibrium constant for this reaction is called Ka, which for acetic acid is 1.8 times 10 to the minus fifth. We began by starting with the concentration of acetic acid, HOAC, is 0.1 molar. We determined expressions for the changing concentration of HOAC, which was minus X, and the changing concentration of H3O plus was plus X, and the changing concentration of OAC minus was also plus X. Finally, we introduced an approximation where we said that 0.1 minus X is about the same as 0.1, which will be true for weak acids, and from this we calculated the pH as being 2.87. That concludes this video where we address the pH of a weak acid, acetic acid. You could apply the same method to other weak acids, at least other monoprotic weak acids, if you know the Ka, if you know the initial concentration of the acid form. Thank you very much.